Hello everyone, I'm Suzana. I'm from Chemical Engineering Department and also Higher Institution Centre of Excellence, Centre for Biofuel and Biochemicals, Universiti Teknologi PETRONAS. Today, I'm going to share about our green and sustainable innovations through process intensifications. My presentation outline will cover our motivations, our case studies, and way forward. Our motivations is we are hoping that through these innovations, it will help to offer solutions towards mitigations of reductions of anthropogenic greenhouse gas emissions and also reductions of energy-related CO2 emissions and reductions of CO2 emissions in transportation factor. So with these motivations, the innovation is tapping upon the resources that we have, biomass resources that can be generated, from agriculture waste. And further, if you see the contributions of biofuel and waste towards as a source of fuel, it is only about 9.3%. So how we can further expand these contributions of biofuels and also waste conversions to support the demand of energy in addition to that available from fossil-based fuel. Right. So our case study focuses on biomass conversions to biofuel, in this case, a liquid fuel, and also biomass conversions to biofuel, which is a gaseous fuel, and biomass conversions to value-added product. So the technologies that couple with the biomass conversions to biofuel covers the hydrodynamic cavitation technologies as well as the green diesel productions through catalytic hydroprocessing technology. And further, we explore the potentials of catalytic steam gasifications technologies to enhance hydrogen productions. And by tapping upon the potentials of the CO2 as a solvent, we try to convert the biomass to produce activated carbon and also to improve further the quality of the bio oil and recovery or the extractive of bioactive compounds from plant materials. And in addition to the supercritical technologies, microwave technology also is an advantage where it can be utilized to produce a green solvent and also to support the delignifications of biomass. And this slide shows the concepts of hydrodynamic cavitations that we introduced to convert waste cooking oil to biodiesel productions. And we know in current productions of biodiesel, 30% of the cost is attributed to the production process. So in our case, we are trying to offer a solutions if how can this cost of productions can be reduced by introducing the approach of hydrodynamic cavitations technologies. In these technologies, the mixings of oil and the solvent and the homogeneous catalyst that we use in this process is further enhanced through the formations of cavities, where this will promote the formations of bubble, where when the bubble is collapsed, it will induce a good mixing between all these reactants and the catalyst there. And then with this technological approach, it will help to reduce the limitations towards the mass transfer. mass transfer. And these hydrodynamic cavitation technologies can further be extended not only to produce the biodiesels. The approach, the technology also can be applied to other applications, such as to improve further the food processing. So normally the conventional mixing that being adopted in industry, the mechanical mixing is being used, and through hydrodynamic cavitation technology, it offers an alternative approach to mix the feed, or to mix or to improve further the processed. Right. In another case study where we try to offer an innovations on how we can further improve the productions of green diesels. So in this case, the catalytic hydroprocessing technologies is adopted, where we try to prove the hypothesis if a new solvent, in this case the 1,2,3,4 tetrahydro naphthalene, can be utilized to convert the oleic acid to produce a green diesel in the presence of catalyst. So by doing so, this will help to complement the hydrogens that it needs to for the process to occur. Rather than the hydrogen supplies from external, it is an in situ approach where the process can be further proceed in the presence of in situ hydrogen generation. Another technology is on how we can convert the biomass waste to produce gaseous fuel. This is an approach known as the catalytic steam gasification technologies, where the steam is utilized as a diluent to enhance hydrogen production. If we compare these technologies with the conventional technologies where to produce gaseous product, an approach of combustion is taking place, where it will produce the CO2. But through these alternative technologies, the CO2 emission is being reduced by introductions of adsorbent materials that can help to absorb the CO2. At the same time, enhance the forward reactions where more hydrogens can be produced. So this will help to further enhance the hydrogen productions by using various type of biomass to gaseous fuel. Right. Another technologies that we explore because we were trying to prove the hypothesis of, can we further utilize CO2 rather than let it being emitted to the environment through through innovations from one step activations technologies. Normally, current conventional technologies to produce activated carbon, it involves a two-step approach, where the first step is carbonizations and then followed by activation. So in this case, we are trying to prove, can we use the CO2 at the same time cut short the overall reaction time by utilizing CO2 to convert the biomass to produce activated carbon. And in this case, through this one-step approach, by converting various type of biomass, and we find that it can produce activated carbon with a quality that meets and comparable to that available commercially. And we also have explored other biomass and to enhance to improve further the carbon content of the feedstock that we can leverage upon to produce this activated carbon. So we have explored the mixtures, the binary mixtures between biomass, and we mix with a petcoke and to produce this activated carbon as well. By using this innovation, it offers a greener solutions, and at the same time it helps to convert biomass to value-added products. And another approach that we tap upon the solvation nature of CO2 is where we use this CO2 at its supercritical conditions to improve the quality of the bio oil. The bio oil can be used as a heat source, or it can be also support various applications in the downstream processes. So the advantages of using the CO2 here, it is non-flammable, and then it's a very selective, okay, to a certain compound. Then with that, it will add values to the product quality. Right. And tapping upon the potentials of this supercritical CO2 extractions technology, we explore, okay, if this approach can further extract bioactive compounds that can be used as additive to make the mosquito repellent, or can be used as a herbicides to suppress the growth of paddy weeds. So it shows that through these supercritical CO2 extraction technologies, the extractive of phytol or alpha tocopherol, as well as chirophyllins and humulin is possible through these innovations. Right. And further, the next step is, okay, what if we can still extract the bioactive compounds, but using, we explore another green technologies where microwave assisted extraction technology is applied here to tap upon whether the extraction time can be reduced, and then at the same time, we still get the quality of the product that we want. And this approach we have explored using comparative to extract active ingredients from food trace. And then it shows us that these technologies, by coupling with a green solvent, such as water, it will help to extract the active ingredient, such as imidazole, benzofuranon, phytol, beta-amytin, in shorter processing time effectively compared to when we extract the bioactive ingredients using the spent tea leaf. All right. And this further leveraging upon the process advantage of microwave assisted technologies, we have explored to synthesize a greener solvent, which is known as the LTTM mixtures. This greener solvent, it will help to complement or as an alternative to the conventional inorganic solvent that being used to delignified the biomass. So by using this approach, it helps to offer a solutions where safer handling of a bio-based solvent can be done to in a delignification process of the biomass. And with that, the way forward with all the innovations that we have, we hope in moving forward we can have upscale the technologies that have been developed to a higher TRL through a multi-disciplinary collaborations and engagement with various stakeholders in to transfer the developed technologies to the benefits of the society and industry. At the same time, it will, in a holistic view, it will help to contribute towards the SDG for that supports the good health and well-being, climate change from the utilizations of the CO2, and also to have a positive impact to the life on land and also the life below water. And all this can be realized through partnership for the goal. And with this, I would like to acknowledge the grant providers, our collaborators, and my postgraduate students, researchers that I've been working through in realizing these innovations to help to offer a greener solutions, sustainable through a process intensification approach for the betterment of future generations. With that, I thank you.